Hi Logic students, this video is about the rules that we need to use in order to accomplish the proofs in chapter 7. So remember, a proof is a way to show that an argument is valid by showing that you can write the premises of the argument on numbered lines, and then you can enter more lines so that on each of those lines you put formulae that come from the premises and from previous lines by the rules, until at some point down here on some line at the bottom you get the conclusion of the argument. That shows that the conclusion can be pushed out of the premises by applying the rules of transformation, the logical rules that allow you to go from certain statements to other statements. Now, all the rules that we were using previously are still valid, of course, and we can continue to use them. Remember the handout that I made for you with all the rules. These rules still apply, and some of them are used frequently. They're obviously very, very useful, especially these rules. Things like disjunctive argument, modus ponens, modus tollens, they're used very frequently in logic. So they certainly apply to the new language that we have been using. Take modus ponens. This is basically the rule that if you have a conditional and then you also have the antecedent of that conditional on a different line of the proof, you can infer the consequent. If it rains, I'll bring my umbrella, but hey, it's raining. It follows that I will bring my umbrella. So when you're doing a proof in the new language of chapter 7, you will still apply this rule to derive conclusions and add lines to your proof. For example, if you have a situation like a line that says if f of a, then g of a, and then a little bit further down you have fa, obviously you can infer ga on another line, and you will cite this line, and the rules of MP. Okay, so pretty straightforward, just like you were doing in chapter 6. However, there are some slight complications with chapter 7 because in addition to the symbols of chapter 7 that kind of mirror the logical operators that you were using in chapter 6, we also have the quantifiers. So the quantifiers introduce some complications because in some situations it'll be a good thing to get rid of them. So we need some rules for eliminating quantifiers. And in some situations we will want to introduce quantifiers. So we will need some rules for introducing quantifiers. So in this video I'll show you the rules for getting rid of quantifiers, and then I'll make another video for introducing quantifiers. The two rules that allow you to introduce, to get rid of quantifiers are known as instantiations. It's kind of a fancy word, but here's the first one: universal instantiation. Instantiation simply means that you give an instance, you give an example of something. Okay, so the idea is not particularly difficult, but the term sounds difficult. Let's say that you have a universal statement. Let's take the simplest one, for all x, fx. You can instantiate this statement if everything has the characteristic f. Obviously you can infer from this that individual a has the characteristic f. So from a universal formula such as this one, you can always infer the formula without the quantifier, and you can instantiate to a constant. You may choose A, but it could be B, it could be C, it could be anything, because everything has the characteristic f according to this statement. So from this statement, it follows the A, B, C, D, and so forth have the characteristic f. You can also infer that x has that characteristic. You know that x here is taken as a variable. It ranges over individuals. But if everything has that characteristic, then also x, in the sense of any individual within a certain set, would have that characteristic. And it doesn't matter, you can use a different variable as well. Fy follows from for all x, fx by universal instantiation, just as much as fx. So bottom line, from a universal statement, universally quantified statement, you can infer instances either in terms of constants or in terms of variables. Here's the other instantiation. It's called existential instantiation. Here you get rid of the existential quantifier. Suppose that you know that there's something that has the characteristic f. So what follows from this? That there's at least an individual, call that individual A, that has the characteristic f. Okay, so this works a little bit like the universal instantiation, in that you get rid of the quantifier. But there's an important restriction. This individual must be chosen as a new individual. That is, the constant that you use must not have occurred anywhere else in the proof. So it must not be in the premises, and it must not have occurred anywhere. You're instantiating to a nondescript person that hasn't been spoken of previously in the proof. So if you abide by this restriction, you will use EI, or existential instantiation, correctly. There are two other rules that allow you to introduce a quantifier, and I will explain them in the next video. They're called universal generalization and existential generalization. So in this video we talked about universal instantiation, UI, and existential instantiation, EI. The next video is about universal generalization and existential generalization. I'll see you in the next video.